Greetings and a warm welcome to all the dignitaries present here. I'm Rimpa from Clernet, serving as the allocated session assistant to ensure a seamless experience. Clernet proudly stands as India's most relied upon digital platform, offering a multitude of enriching services exclusively for the doctors. It is with great pride that Clernet serves as a digital partner for this event, and the focus of today's session is vaporizers. Now, I would like to invite Dr. A.L. Meenakshi Sundaram, sir, a distinguished anesthesiologist and a academic leader. Sir has served as Dean and DME at several government medical colleges, including Theni and Stanley Medical College, Chennai. He is a former National Vice President of the Indian Society of Anesthesiologists and has held key positions including Governing Council Member President and State Secretary of the ISA TamilNadu State Branch. So, without further any delay, I would like to hand over the session to you, sir. Over to you. Thank you.
Thank you, Clarinet, for the opening remarks. And I welcome all of you for the 32nd session of Puthukkottai Bhudhan Second Edition. It is really unbelievable that we have crossed 32 weeks and only 20 weeks to be conducted, 20 weeks more. I think it will go till next January. And with all your support and help, we are able to conduct 32 weeks of continuous webinars. That too, this is the second time. 3 years back, we have conducted 152 weeks continuous webinars. Whatever may be the festival, we will be conducting it. And today it is Ganesh Chaturthi. Even then, we are conducting it on the auspicious day. So we are very happy to have all the faculties today. And see, this vaporiser topic is very, very important for the postgraduates and the youngsters. Because however much we read during the postgraduate days, it will immediately evaporate. Nothing will be there. That is the problem. After repeated reading only, we could analyze what is happening. And I'm very happy. Again, the Karnataka state has come to the rescue because they conducted the boils apparatus webinar. And till now, there is only one webinar where we have crossed 1,000 mark. 1,006 people attended that. After that, several times 940, 980, we were struggling. But now, again, the vaporizer topic is taken over by Team Karnataka, and I am very happy to have you here. And our 31st, the last week report, our 31st webinar was on total intravenous anesthesia. It was unique in one sense that the postgraduate Dr. Shruti was from Pondicherry, Puducherry, and the speakers, Dr. Sripriya is from Andhra Pradesh, and Dr. Tushar Chokshi is from Gujarat, and moderated by Dr. Subramania Mahankali from Karnataka. So that is a pan-India, just like a coolie movie. But anyway, that webinar was very good. I am not comparing the movie with my webinar. It is a pan-India and it has clicked very well, and 765 people attended it live. We have posted the YouTube link also. Dr. Shruti, postgraduate, was talking on pharmacology of fentanyl and propofol. And Dr. Sripriya, who is an associate professor of All India Institute of Medical Sciences, Mangalagiri, Andhra Pradesh. She has delivered a talk on pharmacokinetics of intravenous anesthesia. And Dr. Tushar Chokshi, he was talking about TIVA, TCI with artificial intelligence. So Dr. Subramania Mahankali has moderated it very well, and it was unique. And I request all of you to see the YouTube recording. And today we have 3 Devatas and 1 Sar. So these 3 lady power, we are showing the Nari Shakti, and the majority of the webinars, the faculty were from ladies only. And after OG pediatrics, now anesthesiology is invaded by the lady doctors. So most of the time, it is only lady strength. So we are also exploiting that lady strength. They are very dedicated teachers. And we are having here Dr. Sahana. Sahana is a second-year resident from Bangalore Medical College and the Research Institute. So she has done her undergraduate in Gulbarga Institute of Medical Sciences. Even though she is a postgraduate, her interest is in critical care. That is so nice to see, because critical care requires a lot of dedication and 24/7 work. I don't know how Dr. Sahana is going to tackle that, but she is interested in critical care, and she's having a hobby of reading books, not anesthesia books, probably I think story books. So then only they can have it as a hobby. And again, it will be followed by Dr. Shubha. Dr. Shubha is Associate Professor of Chamundiswari Medical College and Institute, Chennapatna. And she has won the Narayani Award in ISACON National Conference 2017. And she has 3 publications to her credit. And she is continuously presenting speeches and various posters in national and state level conferences. And she has been the Yuva ISACON speaker. Even though she is an associate professor, she is Yuva only. So that Yuvati is very popular in Yuva ISACON, and she has participated in ISACON Karnataka also. And Yuva is she is having a hobbies of gardening. So we used to grow students. Madam, in addition, growing plants, and she is interested in classical music. That means we are interested in non-classical music. I don't know, but she is interested in classical music, and we welcome you, ma'am. And it will be followed by Dr. Chaithali. She is also an associate professor in the same Chamundiswari Medical College, and she has 5 publications to her credit, and she has won second place in the National Essay Contest 2024. That is driving sustainability the anesthesia way. So it is a national second prize, and she has also participated in various state and national conferences. And Madam was a faculty speaker in ISACON Patna, and again Yuva ISACON. So she is also interested in singing. So singing means Madam is singing, and who will dance, I don't know. But to her tune, postgraduates will dance, or her spouse will dance. So what we thought, so when so much of woman power is there, we wanted to moderate the session in a good way, and we wanted to have a right person for that. So the right person will be none other than Dr. Ganesan. First of all, I say Dr. Ganesan is one of the handsome anesthesiologists in the country. So that you have to take care. Consistently, he is handsome. That is another point. So he is an professor of KAPV Medical College, Trichy, TamilNadu. And at present, he is the president, ISA Trichy. He was former secretary. I think he has organized so many things. He did his MD in Madurai Medical College. And he was a secretary for 8 years in Trichy ISA from 2014 to 22. And he is organizing secretary of ISACON South in Trichy, and he is a vice chairman Trichy ISACON 2013, and he was a president Sono Master, and he is a faculty in Swasam and Yendran. See, you have to know that Swasam is about that breathing, he will be talking, and Yendran is about ventilators. So he is good at both Swasam and ventilation. So now he is going to ventilate us with his knowledge, and our brain should be perfused, and the knowledge should not evaporate. That is the first point, because these people are going to talk about vaporizers, and he has delivered lectures in many of the ISA conferences in TamilNadu, Puthukkottai, and he is interested in ultrasound guided nerve block, obstetric anesthesia, uro anesthesia, and critical care. And in spite of all this, he will be listening to music, and he plays shuttlecock. We used to say badminton. That he is not playing ball badminton, but he is playing shuttlecock, because he will always act against the wind. So he will kick that, and he is a good event organizer. He is an event speaker. He is an event organizer. So he has organized city branch meetings to South Zone Conference, and I hope in the near future he is going to organize a national conference in Trichy. We will try, and I wish you all the best, Dr. Ganesan. Now over to you. As I promised, I am giving you the stage by 6:10. Thank you.
Thank you, sir. Thank you. Thank you for the introduction, sir. And as you know, as Sir said, vaporizers are a very dry topic, and postgraduates usually postpone this topic, and finally they try to omit the questions. But without the inhalation agent, we cannot deliver a proper anesthesia. Of course, it is being taken over by total intravenous anesthesia in the due course. But at present, without inhalation agents, we cannot deliver any form of anesthesia. And for you to have a proper knowledge about it, you have to listen to many of the speakers who are present here, because whatever you study will evaporate, and whatever you study, you go on with only the wrong concepts. We also were, as postgraduates, struggling to come out of the inhalation agents, the concept of the vaporizers and the physics behind it for a long time. And after organizing many of the workshops like Endiran, we have done the 6th chapter of Endiran. We have some knowledge of the vaporizers, and even now the modern vaporizers we don't have an access to. And only when we get those vaporizers, we'll be having a full knowledge about how these vaporizers evolved and at what stage we are now practicing. And without taking much time, I like to introduce the speakers there. First, for the postgraduate, Dr. Sahana. She's going to talk on the physics behind the vaporizers. I think it's right time for her to start the talk, and we can have the questions at the end, because without the questions, we'll think that you have understood everything or you have understood nothing. Therefore, everybody will have some doubts. Don't hesitate and post it in the chat box so that we can have a good discussion and make you more clear about the subject. Thank you.
Thank you, sir. Good evening, respected faculties and esteemed delegates. Myself, Dr. Sahana, anesthesia resident from Bangalore Medical College. I would like to take the privilege to thank the organizing committee and everyone present here to give me this opportunity to talk in this webinar. My topic today is physics of vaporization. Vaporizer is a device that changes a liquid anesthetic into its vapor and adds a controlled amount of vapor to the fresh gas flow to the breathing system. We know that vaporizers have come a long way in terms of development from the Schimmelbusch mask, which was used long back in 1846 by W.T.G. Morton, to the current era, we have electronically controlled vaporizers like Aladdin casket vaporizer, Draeger Deva, or McCabe vaporizers. Vaporizers are very important part of our anesthesia practice. Why we need a vaporizer? All inhalational anesthetics are liquids at room temperature and atmospheric pressure. So they have to be converted to vapors. This process of converting the liquid form to the vapor form is called vaporization. And as these inhalational anesthetics are very potent and they have to be diluted with the carrier gas before delivering to the patient to ensure the safe anesthesia. Coming to the physical principles, we have to know about the vapor, difference between vapor and the gas, and for that we need to know what is critical temperature and what is vapor pressure and saturated vapor pressure, latent heat of vaporization, specific heat, and thermal conductivity. Critical temperature, the temperature at which a substance cannot be liquefied. No matter how much pressure we have applied, it can't be liquefied. That temperature is called its critical temperature. Above the critical temperature, the substance only exists as a gas. Below the critical temperature, it can be compressed to liquids or it can exist as gas. Below the critical temperature, the gaseous form of the substance is called the vapor. So vapor is defined as the gaseous form of the substance, which is normally a liquid at room temperature and the atmospheric pressure. Gas is a substance which exists only in the gaseous form at room temperature and atmospheric pressure. For example, critical temperature of the oxygen is minus 118.6 degrees Celsius. Above minus 118.6 degrees Celsius, oxygen exists as a gas. But below critical temperature, it can be compressed to liquid or it can exist as a gas. Coming to other property, it's vapor pressure. Surface molecules leave the liquid and enter the vapor phase due to their kinetic energy. These vapor molecules exert the pressure on the walls of the container. That pressure is called the vapor pressure. Saturated vapor pressure. At equilibrium, the number of molecules entering the vapor phase is equal to the number of molecules re-entering the liquid phase. That temperature at equilibrium, vapor pressure at equilibrium or at saturation is called the saturated vapor pressure. As the temperature rises, more molecules enter the vapor phase due to the gain of the kinetic energy, and the partial pressure also increases. So saturated vapor pressure depends on temperature and also the nature of the liquid. So saturated vapor pressure is a measure of volatility of the liquid. In this figure, picture A depicts the liquid and the vapor are in equilibrium. In picture B, on application of heat causes the equilibrium to shift more towards the vapor phase. So the saturated vapor pressure also increases. In picture C, as the temperature decreases, the shift of equilibrium is towards the liquid phase, and also there is decrease in the saturated vapor pressure. The dose of the inhalational anesthetics can be expressed in terms of partial pressure or volume percent. So partial pressure is defined as the pressure exerted by each of the gases is called, it's the partial pressure of that gas. For that, we have to know Dalton's law of partial pressure. The Dalton's law of partial pressure states that total pressure of a mixture of gases is the sum of partial pressure of each gas. Volume percent is defined as number of units of gas in relation to the total of 100 units of volume for the total gas mixture. So it's a relative ratio of gas molecules in a mixture. Volume percent is a ratio, whereas partial pressure is a number. So volume percent can be derived from partial pressure divided by total pressure. For example, in this container containing 100% oxygen at atmospheric pressure. So 760 mmHg of pressure is exerted only by the oxygen molecules. In this another container, it contains oxygen along with isoflurane. According to Dalton's law, the total pressure of mixture of gases is equal to the sum of partial pressure of individual gases. So here the isoflurane is exerting 238 mmHg of partial pressure. So volume percent of isoflurane can be derived as 238 over 760, that equal to 31% of isoflurane, rest 69% of oxygen is exerting 522 mmHg of partial pressure. Here is the saturated vapor pressure and volume percent of commonly used inhalational anesthetics. Isoflurane, it is 238 mmHg, and 31% of volume percent is present inside the vaporizing chamber. For halothane, it is 243 and 32%. For sevoflurane, it is 160 and 21%. For desflurane, it is 664 and 87%. We can see that desflurane is having a highest saturated vapor pressure and is the most volatile among all the agents, and its volume percentage is 87%. So we need to dilute to get the 6%, we need to dilute with the carrier gas. So we require more carrier gas to dilute it to 6%. So it can't be delivered by the conventional vaporizers. So it needs a specialized vaporizers to deliver the desflurane. Next physical property is boiling point. Boiling point is defined as the temperature at which its vapor pressure equals to the atmospheric pressure. Boiling point decreases when the atmospheric pressure is lower, example at higher altitudes. So agents with low boiling point are more susceptible to variations in the pressure. Agents with higher boiling points are less affected by the pressure changes. Here is the boiling point of commonly used inhalational anesthetics. Here we can see it's all ranges from 48 to 58, but desflurane is having the lowest boiling point of 23.5. So it needs a specialized vaporizer to store and deliver the desflurane because it boils at room temperature. Latent heat of vaporization. A liquid heat of vaporization is the number of calories necessary to convert 1 gram or 1 ml of liquid into a vapor. This vaporization process results in heat loss that in turn results in fall of temperature. If the heat is not supplied, the vapor output will fall. So we have to make compensatory arrangement to ensure the heat supply so that the vapor output will not fall. In this figure, the container containing at 20 degrees Celsius oxygen and isoflurane of 31%. When the vaporization takes place, there will be a loss of heat and the temperature falls to 10 degrees Celsius. So the saturated vapor pressure of isoflurane also falls from 238 mmHg to 150 mmHg, and it will correspond to 20% of the isoflurane. Coming to other physical property, that is specific heat. It is the amount of heat required to raise the temperature of 1 gram or 1 ml of substance through 1 degree Celsius. It reflects the heat capacity. It has advantages in materials used must have a high specific heat to minimize the temperature changes associated with vaporization, and also it tells us about the amount of heat to be supplied to the liquid agent for vaporization. Another property is thermal conductivity. Thermal conductivity is a measure of speed with which the heat flows through the substance. So aluminum and copper having the higher thermal conductivity property, so they conduct the heat better. Thermostabilization is achieved by constructing a vaporizer of metal with high thermal conductivity to minimize the temperature changes when the vaporizer is in use. How much liquid does a vaporizer use per hour? This can be derived from the Avogadro's hypothesis. Avogadro's law states that equal volume of gas contains same number of molecules at the same temperature and pressure. So 1 mole of a gas contains 6.023 into 10 raised to the power 23 molecules. This law can also be defined as 1 mole of any gas at standard temperature and pressure occupies 22.4 liters of volume. So 1 gram molecular weight of any gas at standard temperature and pressure will contain 6.023 into 10 raised to the power 23 molecules and occupies around 22.4 liters of volume. So formula will become density into 22.4 into 1000 divided by molecular weight into standard temperature, that is 273 Kelvin, plus T is ambient temperature at which the vaporization is taking place divided by 273. If you calculate it for halothane, density of halothane is 1.87 and molecular weight is 197. If we substitute these values in this formula, we will get 1 ml of halothane liquid will yield 213.7 ml of vapors. If you apply it for isoflurane, it gives 194 ml. Desflurane will give 194.6 ml. CO will give 164 ml. So approximately it is 200 ml vapor per ml of liquid. Another we can get through Ehrenberg-Eisenkopf formula. This formula is also based on the fact that 1 ml of volatile liquid yields about 200 ml of vapor. It is 3 into fresh gas flow into dial setting. So at last, ideal vaporizer should have these following properties. It should be lightweight, it should be robust and durable, it is easy to transport, it should be corrosion and solvent resistant, leak proof, economical and safe to use. It requires minimal servicing, and it should be accurate over a wide range of fresh gas flow, liquid agent levels, and ambient pressures. It should not be affected by heat loss, pressure changes, tilting or tipping. It should be compatible with vaporizers, mounting, and interlock system. These are my references. Thank you.
Thank you, Dr. Sahana. It was a nice and crisp presentation. Actually, we can move on to the next speaker. It's Dr. Shubha. Dr. Shubha, are you ready? Can you go ahead?
Yes, sir.
Yes.
Very good evening to everyone. So now we'll go on to see the classification and functional principles of vaporizers. So as Dr. Sahana quoted, vaporizer is a device that changes a liquid anesthetic into its a vapor form And not only that, it has to add a precise amount of clinically useful amount of this vapor into the fresh gas flow or the breathing system. And we have seen the evolution of the vaporizer starting from Morton's Schimmel Bush mask and ether bottle to Boyle's bottle and to the Tech 5 vaporizers, Tech 4 vaporizers, and now currently we are advancing to the modern vaporizers. So it has been an integral part of modern day anesthesia. So now we look into the classification of the vaporizers. Vaporizers are classified by Dorsch and Dorsch in 1979. So most of the modern vaporizers can fall into both many classifications. So on the basis of classification of vaporizers are method of regulating output, method of vaporization, pressures of gas flow, temperature compensation, agent specificity, and location in the circuit. We'll look into each classification individually. Based on the method of regulating vaporizer output, the vaporizers can be classified into variable bypass and measured flow vaporizers. The variable bypass vaporizers is a flow splitting device. That is, the fresh gas flow is split into two with the help of a rotatory valve. And in case of measured flow, the vaporizer heats up or the anesthetic agent and above the boiling point so that they are in the gaseous form, and then it is metered into the fresh gas flow. Coming on to the variable bypass vaporizers, the gas flows through the vaporizers is split into the bypass flow and the vaporizer flow with the help of a rotatory valve. And this split is called as splitting ratio and is specific for each agent, because for a more volatile agent, the greater splitting ratio is required so that the bypass flow is more. And if the agent has a low saturated vapor pressure, say sevoflurane which has 160 mmHg, the splitting ratio will be lower, that is 25:1, and hence more carrier gas will pass through the vaporizing chamber. And the splitting ratio also depends on multiple factors like the volatility of the agent, temperature, and the dialed concentration. Say all the bypass chambers have thermostat built in, and which is in close proximity to the vaporizing chamber, and can sense the temperature change of the liquid, and hence a fall in temperature will cause more carrier gas to flow through the vaporizing chamber and vice versa. Whereas the rotating valve located at the outlet of the vaporizers is controlled by the operator. Hence, the output of the vaporizers by a variable bypass vaporizers is mainly dependent on rotatory valve and the thermostat present in the vaporizers. The measured flow vaporizers heats up the anesthetic agent to above boiling point so that it enters the gaseous phase, which are then metered into the fresh gas flow. The classical example of this was copper kettle, but it had its own drawback. It easily caused overdose because of lack of safety features. So the current measured flow vaporizers are Draeger Diva and Tech 6 vaporizers, wherein a calculated amount, which is electronically calculated and monitored with the help of CPU, is injected into the patient's fresh gas flow or the breathing systems. The vaporizer output and the dilute gases are dialed separately in case of measured flow vaporizers. Based on the method of vaporization, the vaporizers can be classified into flow over, bubble through, injection vaporizers. Flow over is when the fresh gas flow flows over the surface of the liquid and carries the vapors present in the vaporizing chamber. But this is a classical one without the help of wicks was a golden vaporizer, which is not in current use. To increase the surface area, thereby in order to increase the vaporizer output, wicks were installed. Wicks with baffles system was also installed in many vaporizers so that the vaporizer output can be increased. Next is the bubble through, wherein the carrier gas is bubbled through the anesthetic liquid, and hence it will carry more vapors to the fresh gas flow. Next is the recent one, the injection method, where calculated amount is calculated with the help of CPU, which will monitor the fresh gas flow, MAC values, and the vaporizer output, and it will be automatically adjusted, and required amount is injected into the fresh gas flow or the breathing system downstream. Based on the pressure of fresh gas flow needed, vaporizers can be classified into drawer or plenum vaporizers. Drawer vaporizers are those that require negative pressure for functioning. Usually the negative pressure is the patient's inspiratory pressure. Whereas in case of Penum vaporizers, a positive pressure is pushed into the vaporizing chamber and it helps in the gas to carry the vapors to the patient. So the main significant differences between the drawer and Penum vaporizers are: in the drawer, patient effort is required for the functioning of the vaporizers, whereas in case of plenum vaporizer, gas under positive pressure is required for the functioning of the vaporizers. The negative pressure is produced downstream of the vaporizers, that is by the patient, to draw the gas through the vaporizers in case of drawer vaporizers. And in case of plenum vaporizers, the positive pressure is produced upstream and there is a negative pressure downstream, that is at the level of flow meters. So the gas will carry the vapors eventually. In case of drawer vaporizers, there is a chance of always bidirectional flow of the gases, leading to many other overdose or less doses delivery to the patient. Whereas in case of plenum vaporizers, there is only unidirectional gas flow. Hence, the monitoring is very accurate because the flow is regulated by the flow meters. The maximum we can set is 15 liters. There is not much of variation. Whereas in case of drawer vaporizers, the minute ventilation can go up to 60 liters, and hence because of the wide range of flows, the vaporizer output is always inaccurate and cannot be monitored easily. And the vaporizers for drawer has to be a low resistance vaporizers because the patient has to create a negative pressure against this resistance. If the resistance is high, the patient won't be able to create a negative resistance. Hence, these are low resistance vaporizers, whereas plenum vaporizers have a high resistance. Most of the drawer vaporizers were early used for a vaporizer in circuit for giving anesthesia in the peripheries. So the classical example of drawer vaporizers are Goldman vaporizers, whereas all the recent tech vaporizer, Draeger vaporizers come under the plenum vaporizers. Next, we'll look into temperature compensation. Why do we require temperature compensation? As and when the gas starts evaporating, the latent heat of because of latent heat of vaporization, there is some amount of heat loss happening, which in turn reduces the saturated vapor pressure, leading to reduction in the vaporizer output. So in order to compensate this loss, we need to provide a heat source to the vaporizer so that there is a constant volume of vapor delivered to the patient. Many of the old vaporizers, like Goldman vaporizers, did not have compensation. So they were comes under the category of non-temperature compensated, whereas the temperature compensated can be either mechanical or electrical. We look into it in the further slides. And there's also something called as thermobuffer, wherein for the boils bottle, a jacket was used to preserve the heat. The temperature compensation can be mechanical, which is by altering the splitting ratio, or by giving the supplied heat, that is electrically heated vaporizers like desflurane Tech6 vaporizer, wherein a calculated amount of heat is continuously given by monitoring the temperature of the vaporizing chamber. And computerized thermocompensation is a newer one, wherein it is used in closed loop systems, especially Draeger Diva vaporizer, wherein the fresh gas flow, MAC, everything is monitored and the vaporizer output is calculated and temperature is compensated accordingly. Now coming on to the mechanical compensation, the classical ones for mechanical compensation are bimetallic strip and the metallic device containing a central rod. In case of bimetallic strip, two alloys were used, mainly nickel and brass, which had differing coefficient of contraction and expansion for heat. Thermal conductivity were different for both the metals. Hence, with heat or with increase in temperature or decrease in temperature, the bimetallic strip bends so that it will change the bypass flow, thereby increasing or altering the vaporizer out. In case of bimetallic device containing a central rod, the outer jacket has a low thermal conductivity. Hence, whenever the temperature reduces, the inner rod dips in and the outer jacket pushed up. The inner rod is pushed up. Henceforth, the bypass flow is reduced, increasing the flow into the vaporizing chamber, thereby increasing the vaporizer output. Coming on to agent specificity, most of our currently used vaporizers are agent specific because of the differentiating features like saturated vapor pressure, different latent heat of vaporization, and boiling points. Each vaporizer is designed specifically for each agent, and to prevent also overdose and or awareness, we need agent specific vaporizers like Draeger desflurane vaporizer. Whereas older vaporizers like Goldman, EMO, and OMV or Boyle's bottle were agent non-specific. That is, multiple agents like ether, halothane were used in the same vaporizing chamber. Next, coming on to the location in circuit. Vaporizer in circuit or vaporizer outside the circuit. Vaporizer in circuit are the drawer vaporizers like Goldman vaporizer, which are incorporated either in the inspiratory limb or the expiratory limb of the breathing system. And the patient's negative pressure mainly helps in vaporizer output. Whereas vaporizers outside the circuit are the plenum vaporizers. Now we'll move on to the factors causing variation in vaporizer performance and design modifications. Mainly coming on to the temperature. The liquid agent will cool with time, which will reduce the saturated vapor pressure and hence the vaporizer output. Therefore, the thermal buffering or thermal compensation are employed in all of the currently used vaporizers. There is also something called as heat sink. Heat sink is nothing but the mass of the metal in the body of the vapor has low thermal conductivity, so that it acts as a heat sink that it will prevent heat loss from the vaporizing chamber. The most commonly used metals are copper, steel, brass, and aluminium. Aluminium is used in plenum vaporizers. And some vaporizers, like the Draeger D-Vapor or Tech6 vaporizer for desflurane, use external heat sources to provide additional heat so that the temperature is compensated all the times. And in case of injection vaporizers, the liquid atomizer in the vaporizing chamber is present. So the temperature does not change at all in case of injection vaporizers, and the compensation for loss of latent heat of vaporization is not required. And one more thing about temperature is most of our vaporizers have a thermostat that is accurate only between 18 and 35 degrees. So any temperature beyond this or less than 18 degree will have inaccurate reading. Next, we'll go on to the flow rate. There is something called as flow dependence. The rate of gas flow affects the concentration at the patient end. That is, when there is a high flow, because of the inadequate mixing, there will be reduced vaporizer output. And in low flow, there is flow turbulence and there is increased resistance, and more gas flows through the bypass chamber, and hence there is reduced output. So both at low flows and high flows, there is reduced vaporizer output. So in order to increase the surface area, many other like wicks or baffles or spiral tubes were incorporated into the vaporizers to overcome this drawback. Next, we'll move on to the back pressure changes. There is something called as pumping effect or and pressurizing effect. The pumping effect is also known as Hill law effect, wherein there is reduced vaporizer output at lower flow. Whenever there is a fresh gas flow that is at low flows, because of the positive pressure back into the vaporizing chamber, some of the vapors will go into the bypass chamber, hence entering the bypass circuit as well. And when there is at expiration, that when the pressure falls, both the gas from the vaporizing chamber and from the bypass chamber containing more vapor will enter the patient, leading to altered vaporizer output. And coming on to the pressurizing effect. That is, there is reduced vaporizer output at high flows. Whenever there is a positive pressure, because of the high flow, there will be compression of the carrier gas, which will concentrate it. Hence, at the end of expiration, when the pressure falls, the pressure reduces and volume expands. Whenever the volume expands, the density falls, leading to fall in vaporizer concentration. So this is called pressurizing effect. Next, we'll go on to the liquid levels. Any vaporizer which is overfilled will lead to low vaporizer output. Why? Because whenever the liquid is overfilled, there is less surface area for for contact for the carrier gas. Hence, the vaporizer output is less. And even if the filling is level is too low, say especially in case of sevoflurane, there is reduced output, especially with also high flow and high dial setting. Next is additives and agents. Halothane has thymol that are at 0.01%. This accumulates over time and causes yellow discoloration of the halothane liquid and also of the vaporizer, which was an indication for cleaning the vaporizer. But this halothane also caused sticking of the removable parts of the vaporizer, especially the dial setting. This led to the inaccurate readings. So the vaporizer was clean when the vaporizer was turning to yellow. And another anesthetic agent which we commonly use is sevoflurane. It is prone for degradation, and because of its reaction with Lewis acids, that is metal oxides or metal halides, sevoflurane can get converted into hydrofluoric acid and toxins. Hence, water is added by the different manufacturers in different proportion to to prevent this reaction. And this water can cause corrosion of the metal parts and hence alter the vaporizer output. So we have to be careful whenever we are using sevoflurane vaporizers as well. Next, coming on to the carrier gas composition and gas flow. Whenever the carrier gas has all of our vaporizers are calibrated with either oxygen or air. Whenever we are using other gases like nitrous oxide, xenon, or helium, the vaporizer output will alter mainly because of change in density of the carrying gas. So, and this will alter the performance of the flow splitting valve as well. Then coming on to the gas flow, at low fresh gas flow, the vaporizer output will fall because of increased turbulence and increased pressure. Hence, the flow through the vaporizing chamber is reduced. Whereas in case of high fresh gas flow, again it is the gases are diluted and hence the vaporizer output is less. Coming on to the effects of altitude on the vaporizer. We will see the effect of altitude on two different vaporizers, that is variable bypass vaporizer and dual circuit gas vapor blender. The dual circuit gas vapor blender is desflurane vaporizer. In case of variable bypass vaporizer, it is calibrated at all the vaporizers are calibrated at sea level, that is at 1 atmospheric pressure. When the output concentration will increase in case when there is ambient pressure falls, that is at higher altitudes. However, even though there is volume percent change, the partial pressure doesn't change, and henceforth the output doesn't vary. The dial settings need not be changed in case of variable bypass chamber. If there is a reduced output, it definitely not because of the high altitude. It could be because of other factors like change in density or viscosity of the carrier gas, fall in temperature and higher altitude, and relative humidity. One thing we have to remember is the saturated vapor pressure is not dependent on the ambient pressure. It is dependent more on the pressure. Hence, for variable bypass vaporizer, even at higher altitudes, the altitude per se doesn't cause a change in vaporizer output. And whenever we are giving anesthesia at a higher altitude, you should make sure that the MAC is represented not as percentage, but in terms of either kilopascals or mmHg. Then coming on to the dual circuit gas vaporizer, it delivers vapor as percentage of fresh gas flow. That is, say 1% of the fresh gas flow will go into the patient, is what we have said. Then, irrespective of the way of fresh gas flow or the ambient pressure changes, 1% will keep getting added to the fresh gas flow. So the volume percent doesn't change, but the partial pressure of the vapors will change with respect to dual circuit gas vapor blender. Hence, the dial settings need to be set at a higher level so that we can reduce the chances of awareness to provide the same anesthetic effect. So we have seen all the classification and functional principles of the vaporizers. So what and how an ideal vaporizer it should be is it should be leak proof. There should be no fluid leakage. It should be corrosion resistant. It should be robust and it should be lightweight, economical, and it should be safe to use, and it should require minimal servicing and should be accurate at all times. And ideal is rare to exist, and hence we are in search of many modern vaporizers. And these are my references. Thank you.
It was a very elaborate presentation of all the vaporizers, starting from the evolution, and the classifications are perfect. And you are dealt with everything, almost the flow compensation, temperature compensation, how it's done for each of the different vaporizers and categories. And it's a very nice work were done, explaining everything in a nutshell, in a very crisp manner, taking not much of time. Thank you, Dr. Shubha.
Thank you.
It's next we can move on to Dr. Chaithali Hebri. We have to talk on the modern vaporizers. Hope you'll be talking on the Aladdin, Diva, and all type of vaporizers, which most of us don't have an access to. But we need to have a good idea about how they function, how they can be monitored safely, how is the mechanism going on. Over to you, Dr. Chaithanya.
Thank you, sir. Good evening, everyone. I'll be talking about modern vaporizers, and I thank the organizers for giving me an opportunity for being a part of this webinar session. So the modern vaporizers are integrated into anesthesia workstations, modern workstations. They combine electronics with pneumatics for high accuracy and safety. They include alarms for malfunctions, deliver precise vapor output, even with changes in fresh gas flow, and can control potent or low boiling agents reliably. Advanced systems allow targeting of end-tidal anesthetic concentration with precision. One of them is Tech6 vaporizer. So as a previous speaker, Dr. Shubha has spoken about classification. For any vaporizer, we need to actually know the classification properly. So the Tech6 is a plenum vaporizer, dual circuit gas blender. It's thermally compensated, it is agent specific, and it is situated out of system. So we need to know why desflurane requires a special vaporizer. The first speaker, Dr. Sahana, has already mentioned it, but I'll just mention it again. The saturated vapor pressure of desflurane is 664 millimeters of mercury and at 20 degrees Celsius, and it has a low boiling point of 22.8 degrees Celsius at 1 atmospheric pressure. So if we use a standard vaporizer, the output would be dangerously high and unstable, and it will require a high fresh gas flow so as to dilute it. And then even a slight changes in temperature can cause large fluctuations in vapor pressure, leading to unstable output. So how does this Tech6 actually work? It's a gas vapor blender which contains two independent circuits. They are arranged in parallel inside the vaporizer. It has two circuits, that is the fresh gas circuit and the other is the vapor circuit. The fresh gas actually passes through a fixed resistant and then moves on to the vaporizer outlet. The vaporizer circuit has a desflurane sump which is maintained at 39 degrees Celsius, and there is a pressure regulator. As you can see, there is a pressure regulator between the two circuits which actually maintains the pressure. The pressure difference between the two circuits is actually transmitted to the control electronic system, which regulates the pressure regulating valve in the vaporizer circuit. So actually the desflurane gets the vapors are formed and then passes through the second that is this resistor, which actually adjusts the concentration by the anesthetist, and then it actually moves on to the vaporizer outlet. So the fresh gas flow moves on through this circuit, and the desflurane actually moves through the other circuit, and then they meet at the vaporizer outlet. So what are the specifications of Tech6? So the agent and concentration. So desflurane we can adjust in a range of 1 to 18%. The capacity of The vaporizer is 450 ml, and it has a SAF T-fill mechanism filler configurations designed to prevent accidental vapor release and enforce correct desflurane filling, and has a LED display. So we can get to know whether there is any low agent, warm up, or if it is operational, and a low battery. So it requires almost 10 minutes for before when there is just switched on to get operated, because the vaporizer has to get heated up. And what is the difference between the Tech 6 and the Tech 6 Plus is it has an advanced LED display, and it is equipped with a self-check. That's the only difference between the Tech 6 and Tech 6 Plus. So then moving on to another important vaporizer, it's the Aladdin cassette vaporizer. It contains interchangeable agent-specific cassettes and has electronically controls, and it electronically controls the gas flow and vapor concentration. It is used in the modern anesthesia workstations, that is Datex Omeda and GE ISIS anesthesia workstation. So classification of Aladdin cassettes is it's a plenum vaporizer. It's a variable bypass, acts as an injector when cassette contains only vapor, and it's flow over with wicks. It is electronically temperature compensated. It is situated out of the system. It is agent specific and color coded. So this is the Aladdin cassette, and this is the front view of the Aladdin cassette. It has a filling port and a prismatic glass which shows the agent, how much agent is there. This is the handle for the release and how to insert, and it actually has 5 magnetic sensors and 4 copper temperature sensors situated internally. So this is the back view of the Aladdin cassette vaporizer. It has 2 ball valves. One is for the inflow and one is for the outflow of the vapors, and has a temperature sensor. So this is the vaporizing chamber of the Aladdin cassette. It has wick-like material, which is in the form of lamellae, and it also has metallic baffles. All these actually increase the surface area, and it also has a temperature sensor, pressure sensor, and liquid sensors, which are present in this vaporizing chamber. Apart from all these, the Aladdin cassette has a CPU, which gets its input from the concentration control dial, flow meters, the flow sensors from the bypass chamber, and also the sensors from the pressure, temperature, and liquid sensors. So how does it actually work? So basically, this is the fresh gas flow. It enters through the bypass chamber, and then into the it passes through the mechanical one-way valve, and then into the electronic inflow one-way check valve, and then into the cassette through these ball valves, which I had shown earlier. And the fresh gas flow picks up the saturated vapors, and then moves on to the outflow check valve, and then into the proportional valve, and mixes with the other gases in the outflow flow meters, and then it passes through the common gas outlet. This is how a Aladdin cassette vaporizer works. And the output of the anesthetic agent is basically dependent on 2 pressures. One is the mixer output pressure and the cassette pressure. So if the mixer output pressure is less than the cassette pressure, what I mean is if the cassette pressure is more, what happens is the fresh gas flow is bypassed and doesn't enter the cassette at all. The inflow valve is closed. So the fresh gas flow just enters the bypass and just leaves without even entering the cassette. So later on, what happens is there is a pressure relief valve. Through this, the pressure is released, and then once the pressure of the mixer output is more than the cassette pressure, then the fresh gas flow enters through the cassette and picks up the vapor and then leaves the cassette and then into the common gas outlet. So what is the difference between desflurane, Aladdin cassette and the other vaporizers is, if the temperature is less than 22.8 degrees Celsius, then it acts as flow over variable bypass. If the temperature is more than 22.8 degrees Celsius, it acts as an injector. That's the difference between a desflurane Aladdin cassettes and the other agent Aladdin cassettes. So what are the advantages of these Aladdin cassette vaporizers? The vaporizer output is not influenced by atmospheric pressure changes, and it has an electronic control. So automatic record keeping and usage calculation is very easy. And it has agent control. That is, the level of the liquid agent will be monitored every 20 milliseconds. So, and then it is lightweight. Tilting is allowable in these. The only disadvantage is it requires a constant power supply. So moving on to pressure, the measured flow injector vaporizers. In this, the liquid agent is held in a separate pressurized chamber and injected into the carrier gas flow. It helps in rapid titration. And it is very commonly used in cases of low flow anesthesia, because even with low flows also, we can use this because the titration is very easy. It is used in high-end anesthesia workstation, that is Macket Flow 1 and Draeger's. So moving on to Macket injection vaporizer. So the classification is it's a plenum vaporizer, measured flow. It's an injector vaporizer. It is situated out of system and it is agent specific. So how does this actually work? So this is the filling port. This is where the drive gas, and this is a fresh gas inlet, and this is a fresh gas outlet. This is the vaporizing chamber. This is a chamber containing liquid anesthetic agent. And this vaporizing chamber has a temperature sensor, and the temperature compensation is done mainly through the feedback from the CPU, that is a central processing unit. So from the drive gas inlet, the driving gas will pass through this at a pressure of 120 kilopascal. This pressurizes a liquid anesthetic container, and then liquid anesthetic passes through this, and a vaporizer injector injects through this vaporizing chamber. So this chamber is heated. So the fresh gas flows through this fresh gas inlet, picks up the vapor, and then leaves through the fresh gas outlet. So in this, the feedback mechanism is by it has a gas analysis line which monitors the output. It has an optical sensor which monitors injection integrity, and it also has a micro sensor which actually controls the pulsed injection of the volatile anesthetic agents. So the next vaporizer is the Draeger Diva, that is direct injection of vapor anesthetic vaporizer. So the classification is it's a plenum vaporizer, measured flow, injector, agent specific. It is situated out of system. It has a target. It is used in targeted controlled anesthesia with closed loop quantitative control. So it has actually two modules. One is the metering module. This is the metering module, that is metering module or vaporizing module. And then it's the gas supply module. So once the vaporizing module is placed it's placed in the slot, there is integration with the gas supply module, and a propellant gas actually enters the metering module and drives the liquid anesthetic agent into the liquid gate, as you can see, and then into the anesthetic dosing chamber and into the dosing valve. So the based on the set concentration, whatever we have set, the dosing valve actually injects the anesthetic agent into this vaporizing chamber, and then the vapors move into the flow sensor and out of the and it is moved out into the exits the metering module. After this, there are actually two pathways. So the fresh gas control mode and auto control mode. So in fresh gas control mode, the fresh gas flows into the mixing chamber and then mixed with the vapor and then into the breathing system. Whereas in auto control mode, the vapor is directly injected into the breathing system and later on it mixes with the fresh gas flow. So what are the salient features of these two injectors? So the vaporizer actually shuts off with an audio-visual technical alarm when there is a malfunction of temperature and pressure. And it is not vulnerable to tipping, and as it does not have wicks to saturate, and the agent cannot spill into the vaporizing chamber. The filling of vaporizer can be performed while the vaporizer is in use, though the agent delivery does not happen during the filling. So what exactly is this closed loop quantitative control, which I had mentioned earlier, is that it's an advanced system where the delivery of volatile anesthetic agent is continuously measured and automatically adjusted to maintain a precise preset end tidal concentration in the patient. So it has three components, that is input, controller, and feedback. So the input is the desired anesthetic concentration, which is set up by the anesthesiologist. And the controller is the vaporizer with the electric control unit. And the feedback is the patient's real-time anesthetic concentration, that is the end tidal concentration of the anesthetic agent. The measured value is continuously compared with the set target, and the controller adjusts the anesthetic delivery. So what are the examples of these? The examples are the Draeger Diva, which I already mentioned. In this, it electronically controls the injection of liquid anesthetic directly into the fresh gas or breathing circuit, and they employ a closed loop feedback with gas analysis. Aladdin cassette actually follows semi-closed loop manner because it works with electronic control and the feedback. So the next device is Anaconda device. It's actually a miniature anesthetic vaporizer with a HME filter. It is used in ICU sedation and it is used in outside operating room settings. So this actually has a ventilator inlet and a patient end. This patient end attaches to the endotracheal tube. All these, the ventilator end and the patient end are in parallel to each other so as to maintain a laminar flow. It's actually oval in shape, and it has a 50 ml syringe in which sevoflurane or isoflurane is attached to this end, to this pump, and then it is attached to the evaporator rod here. So, and it has a functional bilayer that is a porous polypropylene layer, which actually prevents viral and bacterial contamination, and activated carbon, which absorbs and reflects anesthetic vapor and moisture. It also has a gas monitoring port, which actually monitors the end tidal concentration. So how does this actually work? So during inspiration, the fresh gas is picked up, the fresh gas picks up the vapor from the evaporator rod and delivers it to the patient. And during expiration, the unabsorbed anesthetic vapor is trapped by this activated carbon filter. Actually, up to 90% of this vapor is recycled and reflected back to the patient during the next inspiration. So what are the advantages of this? The recycling of vapors reduces anesthetic consumption. It minimizes atmospheric pollution by limiting waste anesthetic gases. What are the limitations of this is it increases physiological dead space. And the reflected vapor actually also has carbon dioxide, which again creates to the dead space effect larger than the device's internal volume. And its use in ARDS and other respiratory illnesses is questionable, as it restricts low tidal volume ventilation strategies. So to summarize, the modern vaporizers provide a stable anesthetic depth, minimize environmental pollution, and reduce agent wastage. Their evolution has enhanced precision, safety, and efficacy in modern anesthesia practice. These are my references. Thank you.
Thank you, Dr. Chaithali Hebri.
Thank
I
you, sir.
think we have some questions in the chat box. It would be nice for the speakers to address the questions.
Dr. Chaithali, you stop your share screen.
The first question is from Professor ALM. If desflurane requires a special costly vaporizer, what is the advantage of desflurane? Why is it used? I think Dr. Shubha be the right person to answer, or Dr. Chaithali, you can take this.
So it is costly, yes, but the induction would be faster. So it is better to use it. The induction is always faster with this.
Recovery, madam.
Recovery is also induction and recovery, sir. Yes.
So you feel that increase in cost is worth to use desflurane, is it?
But nowadays the carbon footprint is more, so that is also another question which we have to address. So right now the desflurane usage is actually coming down, sir.
Yeah, busy. You have to deliver the message to the postgraduates. If suppose desflurane is not there, there will be funk. So you have to say if sevoflurane is available, then what do you stress? You stress on desflurane.
No, sir. Sevoflurane is better.
Okay. So induction is rapid means within seconds. If you induce within seconds, if you recover, what is the best thing you are going to have? So previously, when people used to ether, they used to disconnect. They used to switch off the ether vaporizer long before the surgery is over. It is only your expertise. Anyway, advance in anesthesia management is to be utilized. But I want even that cost constraint for fancy, we are not supposed to use. So that is the idea I wanted to give the postgraduates.
The next question, how are pressurizing and pumping effect overcome? I think Dr. Shubha can go ahead with the answer.
Sir, mainly the pressurizing effect and pumping effect were more common with the older vaporizers. The newer vaporizers have one-way check valves and the bypass chamber buffering. So any sudden pressure change is absorbed by the bypass pathway, not by the vaporizing chamber.
Madam, you please
Henceforth,
switch on the video. Madam, you please switch on the video while talking.
henceforth, there is reduced chance of pressurizing and pumping effect with the use of bypass chamber buffering. And also the splitting ratio devices are there, sir, which will help make sure that only the regulated amount of vapor is into the fresh gas flow. And because of the pressurizing effect or the hill-low effect, there won't be no extra vapors into the fresh gas flow.
Moreover, the presence of an IPP assembly making a long tube prevents the gas while ventilating from the patient side to enter into the evaporating chamber, apart from the check valve. That will also the answer. The presence of an IPP assembly in the vaporizer will prevent the gas from the backflow. It takes a long route to enter into the evaporating chamber, therefore cannot enter and take more vapor during the next cycle. Right. And our next question, what are the safety features in vaporizers?
Sir, one is interlock systems that which will prevent one vaporizer, more than one vaporizer being turned on at the same time, leading to overdosage. And the other feature is key filling system. Color coded and screw specific key filling system are there, so that which will minimize the risk of agent contamination. And also the presence of temperature compensation like bimetallic strip expansion chambers and all will reduce the varying output. And presence of concentration dial lock is also useful, sir. Whenever not in use, accidental turning on or unintended vapor delivery is reduced. And there is also some feature like low fill protection. All the electronic especially Aladdin cassette will show alarm whenever the vaporizer inhalation agent level is very less. So they give alarm, and there are coded sensors, so that will prevent low output.
And moreover, you have a T mode, transport mode in most of the modern vaporizers, where when you want to shift the vaporizer from one workstation or one boils to the other boils, accidentally overspill of the vapor can occur. And during the next ventilation, you can deliver dangerous high concentration of vapors. Even if you accidentally pull the boils apparatus or the workstation, some accidental spill of the vapor can go out of the vaporizing chamber. And in the next cycle, the patient may get the 10 times or 5 times or more what is set on the dial. Therefore, if you can turn on the transport mode or shifting the vaporizer, that too has to be done even after emptying the vapor from the vaporizers. And for tech, we have got a second lock because the MAC value of tech is almost 5% to 6%. And you got a second lock when you turn on anti-clockwise, you have a lock at 12%. You have to again release the lock before going on to 13 or 14% in Tech 6 vaporizer for desflurane. And have you ever used injection vaporizer? Do you find any advantage? I think it can address to Dr. Chaithali Hebri.
I have not used injection vaporizer, sir.
There is another, madam, there is another question connected to that. What is the advantage of injection vaporizers over tech vaporizers, and what is the cost?
So obviously it is a very costly affair, but only advantage of having an vaporizer is it's very useful in low flow anesthesia, and it is very easy to titrate, because the cost of the anesthetic agent will come down, because even the low concentration can be used. It's kind of an only that is the advantage. Other than that, nothing.
See,
Costing-wise,
again, the message is even at the associate professor level, they have not used injection vaporizers. Even at the retired professor stage, I have not used injection vaporizers. So the postgraduates need not lose their heart just because something is not available. What is available is the best. That is the
yes,
message I want to give.
yes, sir.
And the next question, what happens if Tech 7 or Tech 6 and Tech 5 vaporizers are tilted and shifted? That is already, I think we have answered, because when you tilt and shift, the accidental spill out of the vaporizing chamber can happen, and naturally that we have already finished. And regarding the cost of the vaporizers, the Tech series usually, other than the Tech 6 for desflurane, the cost is around some 85,000 to 1.1 lakh or 1.2 lakhs based on the companies. And for Tech 6, I think they charge at 3.25 to 3.5 lakhs, Tech 6 for desflurane. Maybe the injectables, what I heard from the company people, they are charged more than 5 to 6 lakhs. The Aladdin and other case vaporizers. But they have been employed in workstations which are costlier, maybe around 30 lakhs. Proportionately, the cost is same when we use a normal workstations, where the cost is only 6 lakhs for the workstation. We use a vaporizer of 1 lakh. For a workstation of 30 lakhs, 6 lakhs seems to be reasonable on their part. But as Sir said, and it depends on the anesthetist who monitors the patient closely. You cannot sit and go away. You cannot depend. You have to mix and match based on the patient dynamics and depending on the need of the surgery and the recovery. And you have to be there. Therefore, these are an assistance, but what matters much is the anesthetist.
No, actually, I asked one hospital whose ICs from the Trager, I think it cost 45 lakhs. I asked the HOD anesthesia, it's a private medical college, sir, why you have purchased this machine? because which I cannot even imagine in a government hospital. Why you have purchased? And he says, I have purchased it only for the thesis of the postgraduates. Some 5 or 6 postgraduates are doing thesis on that. They are not employing it regularly because it is only in one theater. So all the other theaters, how they are managing? But I say they have just to say that they are having a machine of 45 lakhs. They have, but literally I am also interested in having advanced equipments which reduces the workload of anesthesiologist. But again, every time a new machine comes, we have to read it as a CME. We have to attend so many swasam, endurance. Every time it happens, once I finish, I am mastering it, another new machine comes. Again, they say this is vapor pressure like this, injection is like this. So anesthetists are continuously updating and reading, but it is not employed the same way. Now with artificial intelligence, I think so many intelligent machines have come. Again, we have to read what is artificial intelligence, what is employed. Again and again, we are reading. Again, we say at the end, the eternal vigilance is on the part of anesthesiologist. That is the idea. But we have to read the advances, but we have to know how to manage it with the available resources. So that will be applicable everywhere.
I think we don't have any more questions, sir. And there are want any more discussions to be done, we can proceed on.
If you want to pass your concluding remarks, you can do that. Or if any faculty wants to say something which they have missed, they want to add, they can do that. Or else we can request the ClearNet platform to conclude the session.
And Dr. Shubha, if you want to add anything on the postgraduate part of the basics of the vaporizers, like the physics of the vaporizers, you can go on. If you want to add anything of the PG topic, if you want any highlight any points regarding the basics of the vaporizer or the physics of the behind the vaporizer, you can add on.
Sir, mainly for a PG, the temperature compensation is important, and the functioning principle of each vaporizer, especially the variable bypass vaporizers, Tech 5, 7, which we commonly use. Even they have to know for the exam purpose as well, and also for the exam regular use further as well. So that has to be concentrated, especially when they are reading, and it is the most difficult and confusing part when they are reading. That they have to concentrate, sir. And
And one more point to add, actually the variable bypass involves only a very small amount of the total gas to go into the evaporation chamber, because allowing every gas to go into the evaporation chamber to pick up almost 30% of the vapor output. But the clinically possible dose for isoflurane can be only 1.2% MAC value. What happened in the one hospital? What happened? They actually broke isoflurane bottle. They, in order to hide it from the hospital owner, they closed the OT door and they started wiping the isoflurane. You imagine how much of vapor output would be there. At one point, both fell unconscious and hardly they had 1 or 2 breaths. Actually, one person entered the OT and found out that so much of vapor is there in the OT. Therefore, they inhaled everything and they became unconscious and just they were gasping. They had to do an amber bag resuscitation and then to bring out the OT, open the doors and windows and everything. And finally, they were able to make them survive. It implies that the vapor output is enormous amount. Therefore, only a small percentage of the total gas is allowed to enter into the vaporizing chamber. That is the basic principle of the variable bypass.
So actually, when I was a postgraduate, the teaching was at that time we will have all the vaporizers, ether bottle, Goldman, Tech 3, Tech 4, everything was there. So routinely in the examination, they will show one vaporizer and they will ask what is the advantage of this vaporizer over that. At the time we used to teach the students, they have to say 5 points: flow compensated, level compensated, pressure compensated, time compensated, inversion compensated. So this 5, whenever some vaporizer is given to you, you please identify how many things are compensated in that. And mainly that inversion compensated, even a question has come, if it is tilted, what will be there? So these 5, all the youngsters, mainly postgraduate, have to answer in the examination.
And Dr. Chaithali Hebri, you want to highlight any points on the Tech 6, which you feel that you have left out or it's important for the postgraduates?
Sir, actually, they should know, the students actually should need to know how the working is, and the how it has to be switched on prior to starting, and it will take some time for it to work. All those things they have to know in practical, sir, which I have
And
actually not mentioned.
okay. And the vaporizers is heated to 39 degrees centigrade.
Yes.
Somewhat. But the boiling point is very less. What's the purpose of heating it to 39 degrees centigrade if it even boils at lesser than room temperature?
So actually, 39 degrees Celsius, the vapor pressure will be around 1300, sir, 1300 millimeters of mercury, and it will be at a 2 atmospheric pressure. So it will be easy for the vaporizer to control the vapors during these things. So that's why it is heated at 39 degrees Celsius.
Yeah. Telling it the other way, actually the normal atmospheric pressure is 1 atmospheric pressure. Therefore, the liquid boils maybe at 23 or 24 degrees centigrade. When you construct, they put the vapor in an vaporizing chamber where it is at 2 atmospheric pressure, the boiling point is even brought higher. Boiling point is brought higher. Maybe it could be around some 42 degree centigrade. We do not know exactly. Therefore, you have to have a constant vapor output. You heat at 39 degrees centigrade, and therefore, even as you know, the MAC value of this is 6%, and sometimes you may need up to 8%. Therefore, high vapor output is needed. Therefore, you know the boiling point is very low. It can boil at room temperature. You are intentionally increasing the pressurizing chamber to 2 atmosphere to bring up the boiling point and to keep it at 42 degree, and you heat intentionally at 39 degrees centigrade to have a constant vapor output. So in case if you need 10%, abundant amount of vapor is there to be delivered to have a adequate MAC value.
Yes.
Thank you. There's nothing more to add, sir, because the students have to concentrate only on the basic tech vaporizers, and the Aladdin and other Diva and the Anaconda vaporizers are an additional for completion of their exams, because even as we in the far end of our career are yet to have a good hands-on on this modern vaporizers like Anaconda and Aladdin. Thank you for the opportunity, and thanks for allowing me to share this session and having acquaintance to these good teachers. Thank you, sir.
Thank you. So, as a formal vote of thanks, I want to say Dr. Sahana, who has hidden her face now after that wonderful lecture regarding that physics of vaporization. So, she's not delivering the lecture as a postgraduate. She has delivered the lecture as a seasoned teacher. So, I thank her very much, which was followed by Dr. Shubha, who was instrumental in arranging this. First of all, she only coordinated with me, and we are very happy to have the webinar on basics, because everybody wants to deliver a lecture on clinical anesthesia, management of cesarean section, management of meningioma, that way. So you have taken up the basics and the classification of vaporizers. She has delivered in a wonderful way all types of classifications. So she has explained everything in a detail. Thank you very much, madam. And it was followed by Dr. Chaithali, which was a completely modern vaporizer, which I have not seen, she has not seen, but not just like a blind man explaining an elephant, she has not done that. She has explained it in a very good way. Whenever we see an Aladdin vaporizer, then immediately it will come to our mind, her lecture. She has even given that practical picture, tips. So the working principles, everything, these trio have done wonderfully well. And we thank Dr. Sahana. Again, she is ready to show her face. After that good lecture, she has switched on the video. So I thank these trio from Karnataka, Chennapatna and Bangalore. Again, it was well moderated by Dr. Ganesan. So he is a seasoned teacher. So he has shown his prowess in teaching skills. Effortlessly, he was moderating the lecture, and all the four have made that vaporizer lecture to be retained in the brain of everyone. So definitely it will not vaporize. So tomorrow we will come back with the attendee strength and the YouTube link. So definitely it will be serving as a pleasant memory and a teaching tool for the postgraduates and the youngsters. Now I request the clarinet to conclude the session with their concluding remarks.
Yes, thank you so much, everyone, for joining this session. Clarinet is really glad to have all these brilliant people together. So, with all your permission, I'm closing the session for today. Thank you so much, sir.
Thank you.